All right. Last time we spent a lot of time developing those electron configurations. We talked about then translating that information into those electron configuration diagrams. All right. We got a little bit more to do to build on those electron configurations. So everybody take a second. Give me the electron configuration for potassium, and then as well as the potassium ion. All right, and you can use that noble gas abbreviation for both of these. All right, what noble gas are we going to use to abbreviate potassium's electron configuration? Argon. So if we take argon's electron configuration, we need to add a 4s1 electron in order to get potassium. And when potassium becomes the potassium ion, does it gain or lose electrons? Loses electrons. And remember, this is what our electron configuration is telling us, is about all the electrons in the atom. So I need to scratch one of these electrons from my electron configuration here in order to make my potassium ion. It's going to lose that outermost 4s electron, leaving it with just the electron configuration of that noble gas argon. All right, cool. So that's all well and good for those metals, those group 1, group 2 metals. But what about our transition metals? All right. Everybody take a second. Give me the electron configuration for iron. All right, so we got our electron configuration. I did the full one. If you did the noble gas abbreviation, that's fine. But I did the full one here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d6. Remember, we start numbering our D block at row 1. Cool, all right. So now what if I want to make the iron 3 ion? I'm going to have to remove electrons from our electron configuration diagram here. All right, but importantly for these transition metals, we're going to remove the outermost s electrons first, and then we'll remove the outermost d electrons if there are any left over. Hold on a second. This thing is dragging us here. There we go. All right, so we want to remove electrons from the outermost s first. Then we'll switch to the outermost d orbital, or d electrons. All right, so first of all, what do I mean by outermost? Right, those are the highest energy electrons in your atom. So by outermost s orbital, which one of these s orbitals am I referring to here? The 4s, right? So remember, we organize these from lowest to highest energy. And so that outermost or highest energy s orbital would be the 4s. So in order to make my iron 3 ion, I got to get rid of 3 electrons from my diagram here. I'm going to start with those 4s electrons. Those are going to be the first ones that I take out, right? So we're going to remove from the outermost s orbital first. And then if there's anything else that I need to remove, I'm going to pull from that outermost d orbital. So I'm going to need to take 1 away from that 3d orbital. So my final electron configuration will be argons with no more 4s electrons and 3d5. Cool. So for our transition metals, we're going to first remove from those from the outermost s orbital, and then we'll start taking electrons away from that d orbital. Okay. So given what we just discussed there, everybody take a second and give me the electron configuration for the, let's see, what should we do? We're going to do the vanadium 1 ion here. So vanadium's electron configuration would be that of argons plus those 2 4s electrons and those 3 3d electrons. When I do my vanadium 1 ion, I'm going to remove electrons, and which one of these outermost orbitals am I going to remove from first? The 4s. So that takes me down to 4s1, 3d3. Cool. All right, so now we need to talk, we talked a lot about these electron configurations. Now we need to talk about a few exceptions to our filling rules here. Okay, this is also called the D4 D9 exception. All right, and that is because it affects the elements in the 4th and 9th column of the D block. All right, so if we look at our periodic table here, when I say the D block, what elements am I referring to? Those transition metals. All right, this portion of our periodic table right here is the D block. We got these 10 columns. And it is the elements that live in the 4th column and the 9th column that are our exceptions here that we're going to talk about. Okay, so let's pick one of those. We're going to pick chromium, for example. And based on what we learned, what we would expect chromium's electron configuration to be would be that of argon plus these two 4s electrons and 4 3d electrons. That's what we would expect. All right. We're going to take this here and we're going to build one of those electron configuration diagrams. We're going to put in our y-axis of increasing energy. We're going to do a lazy electron configuration diagram where I say, all right, the bottom half of this is just the same as the electron configuration diagram for argon. And then we're going to draw in our 4s and our 3d orbitals here. Okay? Remember, these diagrams are where we make these little boxes to represent our orbitals, and then we fill them in with our electrons. I have one box for my 4s orbital. How many should I have for my 3d orbitals? 5. Cool. All right, everybody take a second. Based on what we learned last class, fill in this diagram with what we with our expected electron configuration diagram for electron configuration for chromium. So I have 2 electrons in that 4s orbital, one spin up, one spin down, right? So one arrow pointed up, one arrow pointing down. When I get to my 3d, these are all equal energy. So remember, we're going to go through and half fill everything, and then we'll go back and double up, but I run out at 4 here, right? So I just have these 4 half-filled orbitals. Okay, but we said that this was our exception. All right, so why is that? Okay, remember we talked about how things like to adopt that noble gas electron configuration. And those noble gas electron configurations, those diagrams are completely filled in. All those orbitals are completely filled in with electrons, okay? So it turns out that there is something extra stable about half-filled and fully filled orbitals. So half-filled and fully filled, what would technically be called subshells. Are super stable. All right, by subshells, I simply mean all of the orbitals of that particular, in this case, 3D here, right? So these 5 orbitals make up that 3D subshell. Okay. So if we look at our diagram here, we have a nice fully filled 4s orbital. But then my 3D orbital is neither half nor fully filled, right? So instead, because there's something extra stable about these half-filled subshells, this electron, chromium's not going to put a second electron in that 4s orbital. It's going to move it up here to that 3D orbital. We got to fix its spin, so that now both the 4s and the 3d orbitals are half-filled. And again, there's just something extra special stable about half-filled subshells. So what we would expect would be 4s2, 3d4. Everybody take a second and give me the actual electron configuration for chromium. based on what we just laid out in our diagram below. All right, now we only have one 4s electron and that nice half-filled 3d subshell. All right, so then just to be clear, all of the elements in D4 will follow that same pattern. Let's do one of our D9 elements. Okay, what we would expect the electron configuration for copper to be would be that of argon plus 4s2 3d9. All right, everybody take a second and give me the actual electron configuration for copper. So copper is 4s1 3d10, right? Instead of having a full 4s and a 3d that is neither full nor half full, it would rather have a half-filled 4s and a fully filled 3d orbital subshell. All right, so these are our exceptions. Again, we call these the D4 and D9 exceptions because of where they live on our periodic table. Okay, and for these ones here, you would expect these to have 2 electrons in their s orbitals and either 4 or 9 in their d orbitals, and instead they have a half-filled a half-filled s orbital and either a half or a fully filled d orbital, d subshell. Cool. All right. So next thing we're going to talk about is going to relate back to these diagrams here, those same ones that we were looking at, our electron configuration diagrams. All right. I'm going to take one from what we did last class. We did oxygen. Okay. And we're going to use this to introduce what are called quantum numbers. All right, and let me just kind of give you the punchline here where we're going with this. This was this electron configuration for oxygen. All right, what we're going to do is we're going to learn about these quantum numbers, and a combination of 4 of these quantum numbers will uniquely point to one of these electrons on this diagram here. All right, each electron has a different quantum number address. So by specifying all 4 quantum numbers, we're going to point to a specific electron in this diagram here. Okay, so let's go through what are our quantum numbers. The first one is what's called the principal quantum number. Use this variable lowercase n. The principal quantum number is one that we've discussed before, right? The principal quantum number is what tells us the relative size of these orbitals. So if we compared these 3 different sized orbitals here, increasing in size, they differ by that principal quantum number, the number out front. So the principal quantum number of a 1s orbital is 1. The principal quantum number of a 3d orbital is 3. It's that number out front that denotes the relative size of that orbital. So our principal quantum number, and the relative size of that orbital. And again, if for example we said 2s, what would be our principal quantum number? 2. And if I said 4p, what would be our principal quantum number? 4. Cool. All right, the next one is what's called the angular momentum quantum number. We use this variable L, lowercase l, for our angular momentum quantum number. All right, and this tells us about the shape of our orbital. All right, and shape of orbital is something that we've discussed before. If I was talking about a 2s orbital, the principal quantum number would be 2, and what would the shape be? A sphere. And if I had a p orbital, what would the shape be? That peanut shape, right? So we had these different ways already of denoting the shape of our orbital. There's going to be a one-to-one correspondence between what we've been calling it thus far and the quantum number. All right, so our orbital name, I guess it's really the subshell name, geez, getting nitpicky. And our value for that principal quantum number, L. All right, so importantly, we got to remember that natural order that we laid out. When we started naming, cutting up our periodic table, we started with S, and then what came next? P, and then what came next? D, and then finally F. All right, if we can remember this natural order here, it's really easy to remember our quantum numbers because they just go in order. S is 0. P is 1, D is 2, F is 3. Okay, so that sort of ordering there is really important, the S, P, D, F. All right, that's what we got to know. We make an acronym, stupid, people, don't, fart, boom, done. Stick in your head forever now. All right, so as long as we got that order, we can remember our angular momentum quantum numbers here. Okay, so now why? Why do we have to put these in a number form? Why can't we just continue to call it an s orbital? Well, remember where these things come from. What are we going to blame all this theory on? That math. And indeed, if you look at that big, ugly math equation, that is our model for an atom. All these variables here, L, correspond to that angular momentum quantum number. Right? That value of either 0, 1, 2, or 3, depending on what shape orbital you're talking to. So all of these quantum numbers are variables in our equation here. That's where they come from. All right, cool. So we got our angular momentum quantum number, our principal quantum number. The next one's going to be our magnetic quantum number. M sub L. But actually, one more thing before we go on. We got to talk about our limits for our value of L here. And this is something that we already kind of know about, because when we start numbering our P block, where do we start numbering? Like this row right here. Yeah, 2, right? This row is the 2p row, then 3p, right? So there's no such thing as a 1p orbital. Likewise, when we start numbering our d rows here, what number would that be? 3d. So there's no such thing as a 1d or a 2d, right? So there's sort of limits to what we can have for our value of L. All right? And importantly, L is going to take on a value from 0 all the way to n minus 1. So depending on what your principal quantum number is, you're limited by your possible values for L. Okay, so these are the only allowed values for our angular momentum quantum number. Okay, so our magnetic quantum number tells us the orientation of our orbitals. What do we mean by that? So let's remind ourselves, when we were talking about that p subshell, we said that there were 3 orbitals that made it up. And what was the difference between those 3 orbitals? They were all shaped the same. They all had that same peanut shape. The difference was their orientation, right? One of them's oriented left to right, the other one's front to back, the other one's top to bottom, right? They're all oriented along these different axes in space here. So these are these different orientations of our same p orbital here. And that's what our magnetic quantum number is going to correspond to. So which one of these 3 p orbitals am I talking about? They will each have a different magnetic quantum number. I have too many damn pages here. Here we go. All right, so our allowed values. For that m sub L, it can take on a minimum of negative L, negative your angular momentum quantum number. All right, and it can take on a maximum value of positive L. Okay, cool. So let's see if we can't break this down for our oxygen atom, right? Each one, those 3 quantum numbers will point to one of these boxes. So for each one of these boxes, let's lay out the N, the L, and the M sub L value. All right, so for that one s orbital, what is my principal quantum number? 1. All right, what's my angular momentum quantum number for the 1s orbital? 0. And remember, m sub L can take on a value of negative L all the way to positive L. So for an s orbital, what's the only possible value that it can be? 0. All right, and so what we're going to do is we're going to label that orbital box with its magnetic quantum number at the bottom, 0. Cool, so everybody take a second, and for the 2s orbital, give me its 3-digit quantum number address. Now n would be 2. L is still 0 because it's an s orbital, which means that my value for m sub L also has to be 0. All right, so I'm going to label this box 0. When we get up to our 2p orbital, 2p subshell, now the value of n is 2, and the value of L is what? 1. So that means my values of my magnetic quantum number. Now I have 3 options. It can either be negative L, negative 1, 0, or positive 1. All right, again, the allowed values of the magnetic quantum number range from negative L, L is 1, so negative 1 to positive 1. All right, so notice how I have 3 magnetic quantum numbers and 3 orbitals in my 2p shell here. So what we're going to do is we're just going to label each box in order here. This first one is the negative 1 magnetic quantum number. The middle box is my 0 magnetic quantum number. And the last box is the plus 1, right? So each one of those magnetic quantum numbers points to one of those boxes in my diagram. Cool, so those 3 numbers alone would point you to one of our boxes, one of our orbitals. But I told you that there was going to be a 4-digit quantum number address, and it was going to point to a specific electron. So those 3 will give you what box you're looking at. And then our last quantum number that we need is what's called the spin quantum number. And they got real lazy and just kept the M, changed the subscript, M sub S. We talked a little bit about spin last time. It's this kind of bizarre property of our, actually all particles. They have this sort of quality where they're spinning around like tops as they're traveling through space. And electrons come in one of 2 flavors. They can either be spin up or spin down. We represent our spin up electrons with an up arrow, and our spin down electrons with a down arrow. All right. And in terms of their magnetic quantum numbers, in terms of their spin quantum numbers, a spin up electron has a spin of plus 1/2, and a spin down electron has a spin of minus 1/2. All right. Why is it a half integer spin? This actually comes straight out of that quantum mechanical theory that we don't actually do any math of. All right. But it turns out that these half integer spins are quite common for our subatomic particles. So if I use a combination of all 4 of those, all right, I'm going to give you a quantum number address, principal, angular momentum, magnetic, and spin, and you're going to tell me which one of these electrons up here I'm referring to. All right, so our address 2, 0, 0, plus 1/2. Everybody take a second and figure out what electron I'm talking about here. All right, so that first number, 2, tells me my principal quantum number is 2. So I'm looking here on my diagram. That second quantum number, 0, tells me I'm looking at which one of these 2 shells? The S. The next one tells me I'm looking at the only box in that S subshell. And then lastly, my spin of positive 1/2 tells me that I'm uniquely talking about this electron right here in my diagram. All right, this one that I've highlighted in blue is the one with our quantum number address 200 positive 1/2. Okay, so again, every electron up here has a unique 4-digit quantum number address. If you were using that big ugly math equation, that's how you would find the wave function for that particular electron. Cool. All right. So let's, for the sake of practice here, let's do one more. I'm going to give you another quantum number address. All right. Oops. All right. 2, 1, -1, -1/2.
What if it's a d orbital?
Well, we'll do an example of a d orbital. I mean, it really, yeah, we'll do an example here in a second. Same rules, but yes, we'll do an example. All right, so again, the 2, my principal quantum number. That means I'm referring to over here in my diagram, right? These are the 2 with the principal quantum number 2. The 1 for my angular momentum quantum number lets me know I'm talking about which one of these 2. The P. The -1 is going to refer me to this specific orbital, this specific box on my table, on my diagram here. And then lastly, that -1/2 is the spin down electron in that orbital. Okay? So again, 4-digit quantum number points to one of these electrons up here. All right? Yes, let's go back now to our electron configuration diagram of chromium that we created here. All right, everybody take a second, and I want you to give me the quantum number address of this electron right here. The first 2 should be easy. The third one might be a little bit of a thinker. All right, what is our principal quantum number? 3. What is our angular momentum quantum number? 2. A d orbital is 2. So now our m sub l's. What are our allowed values? Right, so they're going to range from -L all the way to positive L. If L has a value of 2, what's going to be the lowest one? -2. And then you're just going to go in order. -1, 0, +1, +2. And again, what you'll notice is that the total number of allowed values are equal to the number of orbitals in that subshell. And so all we're going to do again is label our boxes in order, starting from that minimum value of -2 and increasing to that maximum value of +2. So my electron lives in which specific box? The -2 box. And then my spin quantum number, +1/2. Cool. All right, awesome. So we got these quantum number addresses. They will point to a unique electron on our diagram. Again, where do they come from? These are the 4 variables in that wave function that help you specify which electron you're talking about in your atom. All right, so the last thing we're going to discuss are what are called periodic trends. right? And what are these periodic trends going to be? These are properties of elements we can determine based on their location on our periodic table. All right, so one of these we've actually already discussed before, and that was electronegativity. Right, we said electronegativity was an atom's ability to pull electron density in a covalent bond, in a bond. All right, when we talked about covalent bonds, when we introduced this concept of covalent bonds, we said that two atoms were sharing a pair of electrons. And then we said, all right, that's a little bit too nice and neat and rosy of a picture. Really, these atoms are engaged in this tug of war over that pair of electrons, right? And certain elements are better at tug of war than other elements, meaning they're able to pull that electron density onto themselves. And which one of our elements on our periodic table is our tug of war champion? Fluorine. Right? And what we said was that everything trends towards fluorine. So our periodic trend is that electronegativity increases going from left to right and increases going from the bottom of the periodic table to the top of the periodic table. All right, electronegativity, these are our periodic trends. Again, everything's pointing towards fluorine. Cool. All right, so electronegativity, an atom's ability to pull electron density in a bond. Remember, we kind of simplified this as our electron tug of war that's going on. And again, our trend is it increases going from left to right across our periodic table and from the bottom to the top. Everything kind of pointing at fluorine. Okay, the next periodic trend we're going to discuss is what's called atomic radius. All right, this is the distance from the nucleus of an atom to its outermost electrons. All right, and all that is just a fancy way of saying we're talking about the size of an atom, right? How big or small is that atom? Okay, cool. So let's clean up our periodic table here because we're going to discuss a new trend. Again, this will be atomic radius. All right. So first of all, let's see if we can think about how this is going to work here. What would we, if we had to guess, what would we think would be the smallest element on our periodic table? Hydrogen. And why hydrogen? It's got the lowest mass. It's got only one proton and one electron, right? So you would sort of assume that these things at the top are smaller than these ones at the bottom that have more mass and more protons, and that is correct. Going down the periodic table, our elements increase in their size. Okay? But if we use that same sort of logic, we would expect that, for example, fluorine is bigger than lithium, and it turns out that that is not the case. Counterintuitively, elements increase in size as we move from the right side of our periodic table to the left. Okay, so actually helium is our smallest element, then hydrogen. All right, so we have an increase in size going this way, kind of counterintuitive to what we would think. So why? All right, we're going to look at a few elements here. We're going to model a few atoms, lithium, helium, and hydrogen here. Okay, and we're going to, we could draw our fancy sphere and peanuts and all that jazz. We're going to go for the more of that Bohr model of looking at an atom. All right, let me just remind everybody what I mean. Where we're just going to use circles to illustrate each of our principal quantum numbers here. All right, so for my, whoops, not that. So I'm going to draw my nucleus here. I'm going to put in one proton, and then I'm going to draw one orbital here that'll represent that 1s orbital. And if I have a neutral hydrogen atom, how many electrons am I going to fill into this orbital? Just one. All right, cool. We're going to play the same game with helium. But now I got to change the number of protons. I'm going to increase the number of protons to 2. All right, now if a neutral helium atom, where is that electron going to go? Where are those electrons going to go? Okay. If I have a neutral helium atom, how many electrons am I going to put in? 2. Cool. All right, so where should I put the first one? I'm going to put it in that same 1s orbital, just like hydrogen. And where do I put the second one? Also in that same orbital. And this is kind of the key here as to why helium is smaller than hydrogen. Is because, yes, I've added an extra electron. But where did I add it? I added it to the exact same orbital, to the exact same 1s orbital. All right? And when I added it, and when I went from hydrogen to helium, I added one electron, but I also added a proton. So now my proton has a charge of 2, and it's pulling on those electrons that are in that same 1s orbital, so it's able to pull on them twice as strong as hydrogen was able to. Okay? I added my electrons to that same orbital, that same size orbital, but importantly, I increased the number of protons. All right, so we added an electron to that same sized orbital, and we increased the number of protons. All right, this decreases our radius because the protons can pull those electrons with more force, stronger. All right, cool. So let's play the same game with lithium now. Lithium, I'm also going to increase my number of protons. Now I have 3. All right, which means I'm going to need to add 3 electrons in order to create my neutral lithium atom. We have our same 1s orbital here. All right, when I start adding electrons to lithium, I'm going to add 1 electron to the 1s orbital, 2 electrons to the 1s orbital. But where does that 3rd electron go? The 2s orbital. And remember, the 2s orbital is now a larger spherical orbital. Okay, so here is my n equals 2. So when I add that electron, all right, yes, I increase my number of protons, but in order to add that extra electron, I have to add a new subshell, which is going to be larger than the existing one. All right, so for lithium, we see an increase in size because that extra electron is added to a larger orbital. Okay? All right, so bottom line is when we get our periodic table and we're thinking about our trends in our atomic radius, kind of intuitively things increase going down the periodic table, but counterintuitively we see an increase going from the right side of the periodic table to the left side of the periodic table. Cool. All right, so before we move on here, I want you to order these elements. I'm going to give you some elements here, and you're going to put them in order from the smallest to the largest. All right, iron, oxygen, neon, and rubidium. Order those from the largest to the smallest. All right, which one up here is the smallest? Neon. Then what? And then oxygen. And then iron. And the largest one would be that rubidium. Okay? Again, I'm going to, just to be clear, I'm going to find my elements on my periodic table. And I have to use this trend here. Oxygen and neon, they're in that same row. But again, things increase going this way. And then if I go to oxygen to iron, now I'm going down. So iron's going to be larger. Same thing, iron to rubidium. I'm going to go down on my periodic table, meaning that rubidium is going to be larger. Cool. All right, one more thing we're going to talk about with atomic radius. It's not so much a periodic trend here. All right. But we want to talk about the atomic radius of ions. All right, and let's start with cations, positively charged ions. And we're going to use lithium since we already did all this work to build our lithium model here. We're going to use our example of our lithium atom. All right, so if I wanted to take this model here and modify it to make my lithium ion, am I going to be adding electrons or removing electrons? Removing electrons. And which electron am I going to get rid of? That 2s electron. All right, so if we look, what's going to happen when I lose this 2s electron to the size of lithium? The size of that lithium ion, is it going to get bigger or smaller? It's going to get smaller, right? You've gotten rid of that really large 2s orbital, and now you're left with a much smaller orbital, all right? Not only that, but what else do we notice about this ion here? We got way more positive charge in the middle, yes, absolutely. So not only do I have that larger orbital that I just deleted, but importantly, I also now have an excess of protons. So it's able to pull at these electrons really, really strongly, making this ion much smaller than the lithium atom. All right, so cations are smaller than atoms, than their atom. I guess we can say than their neutral atom. All right. So what about anions? Okay, let's take another example. Okay, we're going to take an element that forms anions, so we're going to take fluorine. All right, I'm going to have to adjust so that now this is my n equals 1 subshell. Oh, no, it's not. It's n equals 2, n equals 1. How many protons am I going to have to put in there? 9. Fluorine's element 9 on our periodic table. Okay. So if I make my neutral fluorine atom, it has 2 electrons in that n equals 1. And 1, 2, 3, 4, 5, 6, 7 in that n equals 2. My 2s and 2p orbitals. All right, now if I make my fluoride ion, am I going to add electrons or remove them from this diagram here? My atom. And where am I going to add that extra electron? It's going to be to that same, it's going to be the 2p orbital, so it's going to go in that same n equals 2 shell there. All right? Now, I'm going to tell you, anions are larger than their neutral atom. All right, but why? I added this extra electron, but it just went into that same sized orbital. So why is this thing bigger than my other one, than my neutral fluorine atom? Less pull. And why is there going to be less pull from those protons? Because now I have more electrons than I do protons, right? So why do we see this trend here? Now my protons are outnumbered. They can't pull on each of these electrons quite as strongly because there's too many of them, right? So why? Okay, because our number of protons is less than the number of electrons, so they can't pull as strongly. so we talked about periodic trends here. Electronegativity, atomic radius. We got one more to go here, what's called ionization energy. All right, this is the energy required to remove an electron from an atom. All right, if we have a neutral atom, how much energy do we have to put in to pluck off one of those electrons? If I'm removing an electron, am I going to form a positively charged ion or a negatively charged ion? Positive, all right? So what we're talking about with ionization energy is an element going from being neutral to a positively charged ion, to losing an electron. All right, how much energy do we have to put in to get that electron away? All right, so again, we're going to cut up our periodic table here, or rather we're going to put this trend on here. Let me clear all this crap off. And we're going to be talking about ionization energy. All right. So, which elements do we think it would be? Easy to get electrons away from? On what side of our periodic table? The left side. Why the left side? What do we know about these elements? These are the ones that form positively charged ions, right? If we're looking at the other side, at our nonmetals, we do not form positively charged ions. It's the opposite, right? These elements want to accept electrons. They're not trying to give anything away. So indeed, we are going to see an increase in ionization energy going from the left-hand side to the right-hand side of our periodic table, okay? And by increase, I specifically mean more energy is required to remove an electron. All right, so that checks out. Our left to right trend is pretty much exactly what we would expect based on our discussion of ions up until this point. Okay, but what about the top to bottom trend on the periodic table? All right, it turns out that these larger elements, it's easier to remove an electron from because the electrons are so far away from the positively charged nucleus. So what we're going to also see is an increase going up our periodic table. The smaller the element, the more energy required, simply because those electrons are held more closely to the nucleus of those atoms. All right, cesium, it can't even keep track of that outermost electron, right? It's so freaking far away from the nucleus, it's just real easy to pluck that thing off compared to lithium. They both like to form positively charged ions, but with lithium, you got to put in a little bit more energy to do it because the electron is so close to the nucleus of that teeny tiny atom. Cool. All right, so let's just do another example here where I'm going to give you a few elements and you're going to rank them for me. From least to most, least to highest ionization energy. Lowest to highest. Okay. Manganese, strontium, selenium, and calcium. what's going to have the lowest ionization energy? Strontium. Oh, so let's find these on our periodic table. Strontium, calcium, manganese, and selenium. So strontium is the largest and the furthest to the left here. So that's going to be first. What's going to come next? Calcium. Right, still on the left-hand side of the periodic table, but a little bit smaller than strontium. And what's going to come, let's go to the flip side. What's going to have the highest ionization energy? Selenium. Selenium is not happy at all about giving up its electrons. All right, so then in the middle will be that manganese atom. Cool. All right, so our periodic trends, properties of elements that we can kind of compare just by looking at the periodic table. We got 3 of them that we've discussed. The first one we introduced before, electronegativity, right? This tug of war between atoms in a bond. The other one, atomic radius. Atomic radius is a little bit counterintuitive because it increases going down the periodic table, but elements on the left-hand side are actually larger than elements on the right-hand side, so you got to keep that kind of counterintuitive nature in our minds. All right, and then ionization energy, how much energy is required to remove an electron from an atom. Our left to right trend is what we would expect based on what we learned about ion formation, the fact that our metals like to form positively charged ions and our non-metals like to form negatively charged ions, so they don't like to give up their electrons very easily. All right, we also see this trend going from the bottom to the top, where our smaller elements are harder to remove electrons from than these large elements, because those electrons are further away from that nucleus. Cool. And that is our discussion of electrons and atoms. Break.